It's usually the case that our rotating body has some continuous mass distribution instead of being made up of a few particles. In this case, our moment of inertia calculation becomes an integral. So I equals the integral of r squared dm. Or for a three-dimensional body, we take the integral over the volume, and it involves the density. So three-dimensional body, we have I equals the integral of r squared rho dv, where rho is the density, or mass per unit volume. So rho is equal to dm dv. If the body is uniform in its density, we can take rho outside the integral. So if that's the case, we can have I is equal to rho r squared dv. And we'll not bother to do an example. I think this is covered in your calculus class, which you may be taking concurrently. You'll probably do many examples similar to this or close enough that we don't have to cover it here. You can also find some stuff in your textbook, of course. All right, that's it for this lecture. Next lecture, we will talk more about rotating bodies. We'll talk about work in rotational dynamics. We're going to talk about a quantity called torque, and we're going to talk about the ever important angular momentum.